Okay, guys. So, very good evening to all of you. All of you can hear me properly. Can you respond in the chat section once? Fine. Okay. So here we'll be starting the basically this is a demo class on strength of material. Now, when you see this syllabus of basically is, mechanics of material, strength of material for mechanical, right? Here. So here, what are all the syllabus that we need to cover? What are all the weightage will be there? We need to see, right? So here, when you just look at the syllabus part, so first part we have what? Stress and strain, right? That is a basic first chapter will be there. That is what we have to discuss. And then we will be having what? Elastic constant. That is what are all the elastic constant we do have, right? That is what we have to discuss, right? So soon when we will start discussing the strength of material, you will come to know we will be having what? Four elastic constant, right? E, G, K, mu. So one of the elastic constant will be what? Poisson ratio. And then we'll be having what? Mohr circle for the plane stress and plane strain conditions. That is the graphical representation of the what? Stresses. Thin cylinder, then we have what? Shear force and bending moment diagrams. Then we have the bending and shear stresses. Then we have the concept of shear center that is being introduced recently only, that is in 2021. Then we have the deflection of beams, torsion of circular shafts, and then Euler's theory of columns, and then we have what? Energies method. Now here, when you just look at the energy method, that means what? See, based on the strain energy, we can able to find what? Deflection also. Either it can be what? Bending deflection, or it can have what? We have the axial deflections. Any deflection we can find by using what? Energy method, that is strain energy method. Then we'll be having what? Thermal stresses. This thermal stress we will be learning in the first chapter itself, that is the basic elasticity. And then we'll be having what? Strain gauges and the rosettes, the testing of material with the universal testing machine, testing of what? Hardness and impact strength. So these are the complete syllabus for mechanical, right? So here, the important chapter, if I just mark it, important chapters for mechanical, like strength of material part, if I just say, right? So very, very important will be what? The first chapter, that is, the stress versus strain, that stress and strain, elastic constant, right? Stress and strain, elastic constant, thermal stresses. Almost every year you will see this particular one question from this topic, right? Stress, strain, elastic constant, and thermal stresses. Now, the second most important will be what? This shear force and bending moment diagram. Because not only it is contributing to only one chapter, it is related to other chapter, that is bending stresses. As you can see here, bending and shear stresses, right? So until unless you know how to draw basically shear force and bending moment diagram, you will not be able to find bending stresses and shear stresses, right? The third will be deflection of beams. Then we'll be having what? Thin cylinder. After that, we'll be having, of course, in this week you can include the concept of what? The Mohr circle for what? Mohr circle for plane stress and plane strain case. That means altogether principal stresses, right? After thin cylinder, which one you can have? This torsion. Torsion of circular shaft. So these are the most important chapter that we need to fundamentally, you should be having conceptual, understanding from these topics to basically, to solve the question of the gate examinations, right? So here, when you see the weightage, recently when you follow the gate 2023 examinations, there they ask almost what 11 to 12 marks question, right? Some weightage you can say. So on an average 10 to 13 you can just have it regarding mechanical strength of material, right? So that is regarding the mechanical syllabus of strength of material. Now coming to this aerospace part, in aerospace one domain is there, that is structure. In that subdomain is there strength of material, right, along with some other uh, subdomains. So the first chapter will be stress and strain, and then we'll be having what, three-dimensional transformations. Then we have the Mohr circle, principal stresses, right? So once again, when you see the very very important chapters, so the important chapters will be what? The first will be this, once again, stress and strain, this Mohr circles, principal stresses. Very very important chapters, right? The second will be what? Three-dimensional Hooke's law we have, plane stress and plane strain conditions, right? And then we'll be having failure theories, right? Maximum stress theory, Tresca's theory, strain energy, right? Now, here strain energy will be what? Two types, that is shear strain energy. Then we have what? Volumetric strain energy, right? So accordingly, we'll be seeing the theories of failure, that what will be coming in this von Mises theory, what will be coming under maximum total strain energy theory, right? Or maximum strain energy theories. Then we'll be having what? Castiglione's principle. Here, Castiglione's principle, it means what? With the help of Castiglione's principle, we will be able to find the deflections, right? Then once again, we have the statically determinate and indeterminate what? Trusses and beams. And in the last, we will be having what? The buckling of columns, right? So when you write the importance of basically what? The sequence of the chapters that we need to cover, here is stress and strain, the Mohr circle and the principal stress, obviously we have to study. Then important one will be what? Failure theories. Means every year we will be having one question from this failure theories, right? And then we'll be having the deflection, right? Then once again we'll be having what? Buckling of columns. So column you can just, after stress and strain, Mohr circle, you can write this one as on the priority list. Buckling of column. Every year we have the one question, either numerical or theoretical. You will find the question from this buckling of columns. Failure theory, deflection. So these are the very very important. Of course, we will be having subtopic also. It is not like only 4 chapters. We will be learning these subtopics also. But what I'm saying, that these are the important thing. Means if we just see the headlines of the chapters, right? We need to study thoroughly. Now, coming to the weightage part, if you just see the gate 2023, what all the weightage will be there? So, if you see that on an average, basically it varies from 10 to once again 14 marks, right? If I say only strength of material, sometime it can be 9 marks, it can be 12 marks, it can be 11 marks, sometimes it can be 16 marks, very high also, right? If you basically they frame the question from the structure, that means strength of material, right? Except this thin section part, 1 or 2 questions will be there from the thin section also, right? So overall, I want to say that this is one of the important one regarding the structure domain. Whether it is clear? All of you? Deflection of beams. Now, when you see the basically the very first topic, that is chapter number 1, we will be studying here, that is stresses, right? Now, so what do you mean by the stress? See, it's a very basic fundamental thing. And remember, guys, whatever the things we are learning, please try to note it down, right? Even if you are if you are just telling any basic thing also, that may not be useful sometime. But in gate examination, definitely the question will be there from that topic. So be very, very careful. Don't think that we are learning any simple thing or anything, right? Treat every topic as on the priority list. Even though you know that topic, but you try to make sure that after the class you will be learning something new. Now, so when you just read this particular definition of these stresses, when a body undergoes deformations, right, under the application of the external forces, the restoring or the resisting forces is induced within the body. The intensity of the force, that is restoring force per unit area, will be termed as stress, right? Now, here some of you might be thinking, sir, what is the meaning of internal resistant forces, right? And this is what basically the whole logic of understanding or studying this strength of material, right? How to basically understand internal resistant forces, right? So it's totally completely, suppose, for example, if I give the example of solid body, or one rod is there. Now this rod is deformable rod, right? That means if I just apply the load P, if I just apply the load P, what will happen? Suppose this rod is there, which is having a circular cross section. This rod is basically what? Circular cross section of diameter D, and which is having a length L. Now, what will happen if I just apply the load? After application of the load, just tell me what is happening in the strength of material, whether it will deform or whether it will not deforming. This load, whether this particular load will able to deform the material of having the diameter D and the length L. Just think of the case, that is case number 1, that is what we are discussing. Whether it will able to deform. Deformation means right now we are discussing about the axial deformations or elastic deformations, where the relative distance, whatever the distance will be there between the two positions, or basically suppose in a body, this is the body we have, right? And on this body we are applying forces P1, P2. Suppose any two particle is there, and the distance between the particle, suppose in a body 1 and 2, the relative distance between 1 and 2 will be, suppose, delta x. After application of the load also, suppose, what is going to be happening? It may be what? Move to some other distance. After movement also, if you just apply the load, still the whatever the relative distance between 1 and 2 will be there. 1 dash will be here, 2 dash will be here, but still the relative distance will be delta x. Then what you say? This is a rigid body. We also call non-deformable bodies, right? Note down each and everything. Once again, I'm telling you, because on the basis of this word, they basically given one question in gate 2023 aero for 2 marks in the deflection one. So until unless you know the meaning of the rigid body, you will not be understanding strength of material, right? So please make a note of it. A rigid body means when the relative distance of a particular in a body, whatever the two particles are there, 2 points are there, if the relative distance are not changing, right, then particular body will be called as what? Non-deformable bodies or rigid bodies. But when you just consider here in the strength of material, point number 1 is here and point number 2 is here. After application of the load, what is going to be happening? Suppose this member is deforming. By delta L, right? Then what we can have? Whether it is a rigid body or non-deform, whether it is a deformable bodies or non-rigid bodies. Because now the relative position, whatever the relative distance between 1 and 2 is being changed. See, 1 dash is here, that is being fixed, right? But 2 point is earlier here, but now it is shifted to what? 2 dash. So now the relative distance has been changed, right? So this is nothing but what? Deformable bodies, right? So strength of material is nothing but a study of deformable bodies. In strength of material, we will not be basically dealing with the body called rigid body. That is the engineering mechanics, right? In the strength of material, we will be learning only deformable bodies. There will be some deformations, right? If there will be, see, in a particular frame or structure, every body is a rigid body, there will not be any deflections, right? The deflection part will be zero. The answer will be zero for that, right? So even though if answer will be zero, then why you will be studying that one in any topic? Either it may be the axial loading, bending loading, or shear loading, right? So there has to be some deformation while studying under strength of material, right? So make a note of it. Now, based on this example number 1, which I have taken the body, I will be showing the free body diagram, how the internal resistant forces will be developed. The meaning of this, the restoring force or resistant forces. Now, see, note down. Yeah, he is asking that what is the difference between the rigid body and deformable bodies. So here only you can just note down the rigid body. Note on the definition. When the relative position of the particles will remain same, that particular body will be called as rigid body. Or body is said to have after the application of the load. That means whatever the things we are calling, what is the motion that we are calling? That is a displacement, right? Rigid body. When the relative position of the particles is remain same, that body will be called as rigid body. For example, what we can have, rod is there, right? This rod is there. When you just apply the load P, what will happen? It will not be elastically deformed, right? It will simply rotate theta. So what is going to be happening when you think of point number 1 and point number 2? Let me just write point number 1 here, point number 2. If you just take the 2 points on the rod AB, this rod AB is there, which is being subjected to load P. At the ends, the relative position, right? Whatever the relative distance is there, that will remain same. After what? 1 dash and 2 dash, still this distance will remain same. Still this particular distance will remain same, right? It is simply said that this body or this rod undergone what? Rotations, right? Now, in strength of material, if you say the same thing, what is going to be happening? Suppose if I just take the rod which is being subjected to same rod AB, when it is being subjected to load P, and if the deformation will be happening something like this. Now when you think of 1 and 2, now 1 and 2 distance will be changed. Definitely it will change. Now the body is having what? Deformations, right? The body has been what? Bent. So now the relative distance between 1 and 2 will what? Will not be same, it will change. So this particular body will be called as what? Deformable rod. Getting my point, all of you? Because whether you know or not, please make a note of it. We will be studying in the deflection chapter, we'll be studying in all the chapters. We'll make sure that if I give different problem, then how to attack those problems by using this fundamental concept. If this fundamental will not clear, you will ask me, sir, why there is a hinge joint here, why there is a cantilever, right? So all this we will play when we start with the what full course of strength of material, right? So before that, you must be knowing what is the meaning of rigid body and deformable bodies, right? Because any number of question you can frame yourself when you know the fundamental concept, right? I can frame the question like this: spring, I can place it, I can apply the load P, right? Same problem if I give in the deflection. Right now, some of you might have studied strength of material in BTech also, right? If I'll ask you, if I give EI value and all, right? Some of you might be thinking, sir, in this case there might be some bending will happen, right? So no need to solve by using that. Only just because of rotation only you can just find the value of deflections, right? But if I change the condition, cantilever, load P, same spring if I apply, whole scenario will change, right? So before understanding those problems, we must be knowing the difference between the deformable and non-deformable bodies, right? Now, so all of you have noted down? All of you have done with this? Yes. Now, so let me just tell you the meaning of basically internal resistant forces, right? Now, here when I just take the example, suppose I am applying the load P to the rod. Now here when you see, this is the rod, circular rod, which is being subjected to load P, right? It is being subjected to load P. For example, here also if I just apply the load P, something like this, and by the plane I'm cutting the suppose one section plane like this. So by this particular plane, I'm just cutting one, just I'm cutting it, right? Section plane. In the section plane, I'm considering left part and the right part. If I'll be asking you, right, and again I'm saying that this is nothing but circular cross section. Circular cross sections. Here, if I just say, if I'll ask you what is the free body diagram of the left part, then what you will say? The free body diagram of the left part, when you draw, it will be something like this. So here I have applied what? Tensile load P. Now tell me in the left part, suppose you what you are doing actually, right? You are applying the tensile load, right? Whenever, what is the meaning of tensile load and the compressive load? Whenever any load which is going away from the cross section, that is a tensile load. And because of that tensile load, whatever the stress will be generated in the body, that will be called as tensile stress, right? And whenever the body is subjected to what? Whenever any load is coming towards the cross section, that is a compressive load. And because of the compressive load, whatever the stress will be there, that is called compressive stresses. Here, which kind of load we have applied? That is a tensile load. Now, when we apply the tensile load, what are all the actually you are trying to doing, right? You are trying to changing the what? The relative distance between the two particles. That means here, if I say two particle one and two, right? Actually, they are at a distance what? Initially, they are stable in a particular what? Stable conditions at a room temperature. The distance, whatever the distance is there, that is what? Delta x. But what you are trying to doing, you are trying to creating the disturbance in the whatever the distance will be there between the two particles. You are trying to elongating this bond, something like this, with the help of load P between the particle 1 and 2. Then what the particle 2 will say? We have the mutual bonding in a solid body. You know that bonding will be there between the particles, and you are trying to developing what? Tensile load. You are trying to what? Disturbing the relative position of the particles, whatever the relative distance of the particles, two particles in a particular body. Then what will happen? What is going to be happening? What the particle number 2 will say in a body? We will be applying what? Internal resistant forces, right? They will be developing some opposite force. In which direction? In the opposite direction of the applied external load, right? In this direction. What is this? This will be internal resistant forces. Getting my point? Because it is not for the particle number 2. Maybe particle 3 will be there, particle 4 will be there, particle 5 will be there, right? Those who bonded with the some other what? Particles, consecutive particles, right? So whatever the whenever the any forces will try to disturb the inertia of the body, what will the body will say? Right? It will try to oppose that one, right? Whatever the limit or capacity will be there, it will try to oppose that external load, beyond which if you apply huge amount of external load, it will fail. The material will what? Fail. And now that failure will be understanding in the what? Theories of failure, right? Right now I'm saying that we are applying some limited amount of load. We are not applying huge amount of load or very high amount of value of the load. So what will happen? According to that, if you just take summation of forces in x direction to be 0, what will happen? P minus F will be 0. Then P will be what? F, right? Then what we will say? Because of the internal resistant forces, IRF, because of this which is being developed on a particular unit area, we say stress has been generated in the body, right? And we know that from the static equilibrium point of view, that P is equal to what? F. So internal resistant force will be automatically equal to what? P only, right? So if somebody will be asking you whether external forces can able to generate the stress in a body, the answer will be no, right? Definitely stress will be there because of what? Internal resistant forces only, right? If internal resistant forces will be 0, stress will be 0 even though you apply the external load. Getting my point? Tell me, guys. So some of you might be thinking, sir, in a body load, suppose 10 Newton has been applied, so stress will be 10 divided by area will be what? 1 meter square, suppose, for example. Then you will say, sir, 10 megapascal or maybe 10 pascal will be the value of stress. But that is not true. Internal resistance force should be there, right? If not, then it will be 0. What is the example of particular any inertia of the body you are changing and still stress will be 0? Any cases you know? Any kind of load, because load can be any kind, right? It can be mechanical load, it can be thermal load. So have you seen any scenario or any cases where stress will be 0? Still the load is there. Tell me guys. See, when you think of any case of what? Free expansion, right? Suppose a body is there, which is being placed, for example, on a surface, right? And now if I increase the temperature and there is a no support, basically there is no restriction on any side. That means there is a no support is there here and here. There is a nothing called support is there, right? This body is free to expand when the temperature has been increased, right? So what is going to be happening in this case? Tell me guys, whether any internal resistant forces will be developed, because this body which is having coefficient of thermal expansion, this body itself wants to expand, right? And you are allowing that expansion, right? When you increase the temperature, definitely every material will have coefficient of thermal expansion, right? And with the help of that property, every material will try to expand or compress, right? Whether you increase the temperature or decrease the temperature, based on that there will be some what expansion or contraction will be there. So this particular body, because of delta T, whatever the energy we are supplying, that thermal energy we are supplying, based on that, this body is what? Able to expand freely. So this body will not be able to developing any kind of internal resistant forces. So the stress will be zero in that case. All of you are getting my point? Right? Fluids also will not be able to generate any kind of internal resistant forces, but this statement will be not completely true, because when you see the fluids, right, the fluids will able to resist for which case? When you just apply 3D compressive stresses, right? For any kind of tensile stress, it will not be able to generate any internal resistant forces, right? The tensile stress or stress will be zero in the fluids. Getting my point? Tell me guys. No, from where the internal resistant forces basically will be suppressed, right? Suppose this body is there, suppose a body is there, right? I'm just taking two cases, for example. I'm just taking one example number one here, where I'm taking one case, a body is there which is being placed with the fixed support, which is having a length L, right? This body is having the length L and diameter D, for example. What you are doing, just you are increasing the temperature, right? You are just increasing the temperature of the body. What will happen? Whether this body will able to change its length, whether any kind of changes will be possible, any axial or longitudinal deformation will be possible here. Tell me guys, the net deformations will be zero, right? The net deformation will be zero because it is being fixed at both the ends, and whatever the no axial deformation will be there. So here what is happening actually? Whether stress will be generated, yes, the thermal stress will be there. That is not equal to what? Zero, right? So here what is actually happening? Here, because of this, when you draw the free body diagram, it will try to expand initially by the amount whatever the delta L is there, thermal. But because of the support, there will be some support reaction will be there, right? And because of this support reaction, thermal stress will be developed, right? Getting my point? It will try to expand, but this support will say, you just go back. Can't you see that I am fixed? When it is fixed, then how it can able to expand, right? And because of that resistant forces, this body will try to develop what? Internal resistant forces. Getting my point? But suppose the same body is there, for example, if I just take the body, if I simply place it, right? This body is there. If I draw the 3D view of that, L, B, and height is there, H, right? When you try to expand, suppose delta T has been increased, then what will happen? It will simply expand, right? There is a no support, just like that in the first example what we have seen. If it is free to expand, what is going to be happening? The length will be L2. Suppose L1, B1, H1 is there. This B1 will be there. This will be what? H2. Now this see, because of the property, it was actually trying to expand, as you can see, alpha delta TL, right? Don't worry about that. We will be studying in separate, that is thermal stress chapter, right? Right now I'm saying that one formula is there for delta L thermal, this one, right? Because of the property of the material called coefficient of thermal expansion, it will try to expand, but support will offer what? Some kind of reaction forces. Getting my point? The material want to expand, but the support is saying you just go back. Then what the material will say? It will develop some internal resistant forces or not? It will just apply some resistive force or not? That particular support to the support reactions. Tell me guys. But here there is a no such kind of support in the example number 2. Then why the internal force will be developed? That's why the first, this case will be called as what? Free expansion. And because of that, thermal stress will be 0. That means stress will be 0, right? Is that clear now? So without internal resistant forces, there will not be any stresses. Getting my point? Either mechanical stress or thermal stress. Mechanical stress because of the external loading, thermal stress because of what? Temperature changes. Getting my point? If both are acting, then we need to superimpose, right? Along X, Y, or Z. In all the direction, there is no support in the free expansion case. Getting my point? In the first example, whatever the stress will be there in the X direction. In the Y direction, it will be 0, right? Or in the Z direction, it is free to expand once again in the example number 1. So again, it is 0, right? There will be strain, but stress will be 0. Getting my point? All of you, whether it is clear? And whatever the deformation we are learning right now, this delta, whatever we are adding, those are the elastic deformations, right? Within the elastic limit, we are learning this, all the fundamental, what? Strength of material right now, whatever it is going on, right? Once we cross the, basically what? Yield point, when we draw the stress versus strain diagram, after crossing the yield point, right? When you just draw it, when you learn the Hooke's law, in that we will be learning stress will be directly proportional to strain. After that, when you just see, it will be like this. Right? So here ultimate point, then failure point, then there is a basically what? Up to this point, point number A, stress is what? Directly proportional to strain. Then what we'll be having? B point, that is the elastic limit, right? Then we'll be having what? Yield point, C point. Then again we will be having what? From here, this is nothing but plastic deformation. So till this particular part, till B, whatever we are learning, that is the elastic deformations, right? For the elastic bodies. I have explained you, right, in example number 1, that why thermal stress will be there in the case number 1, because whatever the support reaction will be there from the support, whatever the support is there, that is a fixed support, that cannot be the flexible support, that cannot move little bit also, right? That is a fixed support. So definitely it will offer some kind of resistive forces, and because of that resistive forces, the material will try to develop some internal resistant forces, and because of that, stress will be generated. Getting my point? Why it will develop some internal resistant forces? Actually, material want to expand. The moment that material, suppose for example, the material name is some example, what we say X, right? This particular material will see that, okay, temperature has been changed, temperature has been increased. What is my inertia? What is my particle will say? All my particle will say, we will try to expand. But what this support will say? No, you can't expand. because you can see that I am at the fixed position, I cannot move little bit also. So you are trying to opposing that move, basically what the free motion of the particles. In earlier cases, what is actually happening, the body want to say we are at the rest condition, we want to be at the what, don't want to move, don't try to disturb the relative distance between the particles. But what actually you are trying to doing, you are disturbing it, you are just trying to increasing the length of the particles in between the particles. Then what the particle will say, we cannot go like that, we will be developing some internal resistant forces. Because of that, here the stress will be generated, right? Here we will be calling this to be mechanical stress, because it is happening because of what, external load. All of you clear with this? So either we study mechanical stress or thermal stress, it is ultimately the part of the what, stress only, right? The types of stress. Is that clear? So it depends on actually what the state you want to change of a particular body. Suppose a body you want to be under rest condition, you are trying to disturbing it. Once again, it will develop internal resistant forces, right? Now suppose in this case P will be 0, automatically F will be 0, right? You are not disturbing the body, then why this body will develop internal resistant forces? Because you are not changing the temperature, T1, T2, T3, at all the time temperature will remain same, right? At the room temperature. The moment you are heating that material or you are just increasing the temperature, what is going to be happening? The coefficient of thermal expansion will be coming into the picture, and because of that, they will try to expand. And if you are allowing that expansion, no internal resistant forces will be there. You are opposing that, internal resistant forces will be developed, and because of that, stress will be developed, right? So this can be basically framed in a particular MSQ question, right? Already we have seen some of the question in the mechanical. That same question can be asked in aerospace also, right? Is that clear, all of you? And what will be the free body diagram of the right part? What will be the free body diagram of the right part? When you see the free body diagram, correct. So here we are applying the load, and it will try to develop some internal resistant forces like this, right? So my dear friend, here one thing you need to understand, if I draw the normal stress or stress distribution just because of the axial load, because it is being passing exactly at the centroid of that, you know, this line of action of the forces, then we are calling this to be what, axial load, right? Now here one thing you should understand, all the particle number 1, particle number 2, particle number 3, particle number 4 will developing what, equal amount of internal resistant forces, right? Understand? If I just consider unit area, for example, if I just take area like this, if I just take unit area dA, in that also what will be the forces will be developed? Suppose for example the force has been developed, dF force. For example, the force which is being developed on a dA elemental area, in whole area, F force will be developed, right? But for the very very small area dA, what is the force which is being developed? Let's say for example it is dF. Then what we can find, my dear friend? Sigma. Sigma can be found out dF divided by what, dA. Then what we can write? Then what we can write? dF can be written as sigma into what, dA, right? Sigma into dA. Now for example, if I just do the integration, what will be there? What will be there, my dear friend? If I just do the integration, sigma will be coming outside, because sigma is not varying, right? If sigma is not varying, sigma is what, constant, right? I told you each and every particle will develop equal amount of forces, and when you just divide by area, each and every particle will be developing equal amount of stresses, right? Something like this. When you draw the distribution, it will be like this. Axial stress axial stress distribution. Now here you can see sigma is same for all the particles. Sigma I can take outside, sigma into A, that will be the formula. Getting my point, all of you? Or particularly, if I just write for the delta A area, then what we used to write? We used to write like this. Let me remove this part. Rather than writing this df by A, we used to write sigma to be as limit delta A tends to 0 df by A dA, because stress is defined at a particular point. Remember, stress is defined at a particular what? Point. Stress is defined at a point. Now, what will happen when delta A tends to be 0? When delta A tends to be 0, it will become what? Point only, right? When delta A tends to be 0, it will become point, right? Yes or no? Tell me, guys. Correct. So make a note of it. So this is nothing but magnitude of the internal resistant forces which is being developed on a unit area, that is dA elemental area. Right. In examination, suppose for example, they will mention that if I apply the load and stress is varying with some what area, let's say it is being given some kind of function, right? Then what we have to do? Based on the area it is being changing. For example, it is e to the power minus a. It is varying exponentially. Then we have to do the integration to get the forces, or whatever the based on the load. If you want to find anything, then you have to do the integrations, right? Here what we are mentioning, that it is whenever we are applying the load P, that is the axial load, centroidal load, it will be uniform axial stress distribution. Uniform axial stress distributions, right? Make a note of it. Now some of you might be thinking, sir, why the stress is defined at a particular point, right? Now there is a very important thing to understand, right? Stress cannot be simply defined on a particular space, right? It has to be defined at a particular point. At a particular point, a lot of planes are there, right? At a particular, in a body, when you see the body, when you consider a point here, right? And if you just make the elemental on this elemental, if you just show the what stresses, then you will come to know that for this particular point, whatever the stress will be there because of the loading, it will be different for this particular load. For example, here point will be there, point P1, point P2, right? So stress will be keep on changing for the different points. It will not be the same, right? So for understanding those things, we will be what? Defining the stress at a particular point. And at a particular point, if you just consider, suppose a body is there, at a particular point, how many planes are passing? Infinite planes are passing. Yes or no, guys? At a particular point, infinite planes are passing, right? On which plane we are getting what? Maximum stress? On which particular plane we are getting the minimum stress? We don't know. That is what we need to understand, right? If on a particular plane any stress is maximum, that material will fail because of that maximum stress. Getting my point? Suppose you are defining in a space, you don't know any specific plane where exactly the stress is generated, then can you say that material will fail? Even though material is failing, what you will report to the customer? You will say the material is not failing. Getting my point? Whether you're understanding the meaning of defining the stress at a particular point or not. If only one plane would have been, suppose hypothetical body is there, only one plane is there. That is not possible practically, but I'm saying only one plane is there, right? And one particular point is there at a particular point, right? If only one plane is there, then whatever the amount of load you are applying, either P1 like this, or P2 like this, the material will fail only on this plane. Then you know that. Then no need to define at a particular point. You define on this plane only, AB only. But we know that at this particular point, what we call P1 will be not will be have. Let's say that this point is what, B point, and this is nothing but B dash. AB dash is a one plane, but we know that at point B, lot many planes are passing. What is happening on this CD plane? What is happening on this EF plane, right? To know those things, right, in a particular material, the behavior of the material, then we have to understand that stress should be defined at a particular point. Getting my point? Because we might be understanding that, suppose for example on CD plane we'll be developing some maximum stresses, right, not on AB plane, then material will fail because of that plane only. You will say the rupture like this material will fail like this, and you will not be understanding. You might be thinking in this play, if suppose if I keep on applying the load, the materials will fail like this only in a two parts on a AB plane. But suppose the moment you got to know that it is failing along CD plane, then what is happening? CD plane is saying that you don't apply that much of amount of load. Even though you keep on applying the load, you keep on increasing the load, your material may save with respect to AB plane. It may not fail on AB plane, but it may fail on CD plane. Then how you come to know that on CD plane it is failing? When you define the stress at a particular point. Is that clear? Tell me, guys. Now, we will be learning the this particular at a particular point how many planes are there, infinite planes are there. Those things we will be learning when we start discussing the principal stresses, right? There the picture will be more clear. No need to worry about that, right? Now, regarding the directions, when you just think of any directions, right? I think what is the meaning of stress? Whether that particular term is clear or not. Whether you know now the meaning of internal resistant forces, and because of that we know that stress will be generated. Whether that thing is clear? Tell me, guys. Yes. Now, coming to the directions, generally the normal stress pointing away from the plane or a section is considered to be tensile stress, right? While the normal stress towards the plane will be considered as compressive stresses, right? What is the meaning of that? For example, you are applying tensile load sigma. So here at sigma xx will be called as plus sigma. That is a tensile stress. When you see from the left side or right side, when the whatever the stress will be there, when it is going away from the cross section, we say it is a tensile stress. That is a positive. But when the stress will be acting towards the cross section, then what we say, it is minus sigma. That is compressive stress. Getting my point? Tell me, guys, whether this thing is clear. And we also call normal stress, sometime it is basically what? It is also termed as direct stresses. The normal stress will be also called as the direct stress. Now, coming to the notation of these stresses, coming to the notations. Now, some of you might be thinking, why we need only two notations? Why we denote it by sigma ij only? Why not ij k? Anybody know that? Tell me, guys. If you just see the notations, why we are just basically denoting it is by sigma ij, not by ijk. Only two subscripts are required. One will be indicating the plane, one will be indicating the directions. Anybody know the reasons? Now, let's focus your attention on this cubical body, for example, which is nothing but this particular direction is what? Z directions. This direction is what? X direction. And this particular direction will be Y directions, right? So what is happening? When you just look at this particular diagram, yeah. So in this particular figure, if I say sigma xx on ABCD plane, if I say sigma xx like this, so what actually we are saying? What actually we are saying? We are saying sigma xx means what? X is a nothing but what? It is denoting the plane. Sometimes we also call this to be denoting what? Face. This is denoting what? Directions. So how to read that? The normal stress which is being developed on X face in the X direction. This will be the X face. We also call this to be X plane. On which basis we are defining? Because what is the normal, what is the perpendicular axis which is being passing through ABCD plane? All of you guys, please tell me. What is the axis which is being passing through this ABCD plane, and that is a perpendicular, whether Y axis, Z axis, or X axis? Tell me, guys. X axis, right? So that will become what? X face or X plane. In second, whatever the second subscript will be there, that second particular suffix will be denoting what? Directions. In which direction? X direction. That will be like this. Now, whether it is a positive or negative, how you will come to know that? Again, we have to decide based on the directions of what? Stresses, normal stresses. So when you see here, when you focus your attention, what you are understanding, whether it is going away from the cross section ABCD or towards the cross section sigma XX, away from the cross section, that is what? Positive, right? It is acting on a positive X phase in a positive X direction. That's why we are calling what? Positive sigma XX, right? When you think of this, see, the normal stresses, if you see the directions, are defined as positive when they are directed away from their relative surfaces, right? Now, some of you might be thinking, sir, what is this sigma xy and this what we are calling tau xy? What is this, right? Some of you might be thinking what this particular terms and terminologies, right? Now, so to understand that, when you see the stresses, we have the two types of stresses. One will be the normal stress. Second will be shear stress. When the normal stress will be developed, suppose in a body, when you are applying the load which are perpendicular to the cross-sectional area, then which type of stress will be developed? P by area. Suppose area is A. Then we say this to be normal stress, right? The load is acting perpendicular to the area, right? When the load is acting parallel to the area, because of the P2 which is being applied parallel to the cross section, which type of stress will be developed? P2 divided by area. All of you are getting my point? Tell me, guys. All of you are understanding the normal stress and shear stress? Yes. All of you are understanding the normal stress and the shear stress? Correct. Now, some of you might be basically what disconnected the moment I have started my discussion on a particular point. Stress is defined at a particular point, but please be patient, especially in my classes. You need to be little bit patient, right? Each and everything will be clarified when you just will be what after the classes, it will be automatically resolved whatever the doubts you'll be having, right? Sometime I used to discuss the things which are obviously related to the particular whatever the live things are happening, but maybe sometime it will be useful, it will be connected to some other chapters, right? So when I'll be coming to that chapter, the things will be clarified, or maybe that particular subsequent topics, right? Now here, one more thing you need to understand, what is happening, whatever the stress are acting, that is a normal sigma xx, whether it is a normal or say it is a normal stress, right? Yes or no, guys? Whether it is a normal stress or shear stress, normal stress, everybody know that, because it is acting perpendicular to the particular abcd plane. And now what you are thinking, now suppose for example, what about the sigma xy or tau xy? On what basis you can define tau xy? Whether it is acting on a x phase or y phase. This is acting on this which particular phase? X phase. Why you are saying that x phase? Because the whatever the load here load is there, or stress is there, which is being parallel to the area and perpendicular to the this abcd area, which axis is there? X axis is there, right? If that particular axis will be x axis, that will be the what? X phase or x plane. In which direction? In the y directions. Not tell me this is nothing but phase, this is nothing but directions, whether it is positive or negative. So how we can define whether shear stress is positive or shear stress is negative? When it is acting on a positive phase and positive directions, plus and plus will become what? Plus. Positive phase, positive directions. Because what is our positive? What is our positive coordinates? This will be our positive x-axis. This will be our positive y-axis. This will be our positive z-axis. This will be the negative. This will be minus y. This will be minus x, right? This is our standard sign conventions that we used to follow. Suppose for example, if I apply the shear stress like this, then what you will read, whether it is positive, negative, whether it is tau yz, whether it is tau xz. Tell me guys, on which phase it is acting? First suffix, tell me guys, on which particular phase it is acting? On which particular phase it is acting? It is acting on a y phase. Why? Because what is the perpendicular axis which is being passing through this AB EF plane? Y. So y will be coming. In which direction it is acting? In which direction it is acting? X direction. So tau yx will be there. We call simply tau yx. That capital letter. Tau yx will be there. Getting my point? Tau yx. Whether it is positive or negative, it is positive. Because it is acting on a positive phase and positive directions, we are calling that to be what? Positive tau yx. Getting my point? If suppose we are applying like this, for example, if I just denote it by shear stress like this, now tell me, on EF GD plane or what we call GH plane, this particular plane which is being denoted by the red color, and the stresses, that is tau, which is parallel to EF GH plane, tell me what are the notations? Tau, on which phase it is acting? It is acting on a negative x phase. Getting my point? If I just denoted before, tau for EF GH plane, if I say tau on which phase? Negative x phase. In which direction? Negative y directions. Once again it is positive. Negative will become what? Positive. Once again it is positive. Getting my point, all of you? Tell me, guys. Whether it is clear? Negative x phase, because what is the axis which is being passing? Negative x. For this GH plane, which is a perpendicular axis. Perpendicular axis is what? Minus x. Getting my point? All of you. Right? Now, correct. Now, whether if I just denote it by something like this. Yes. If I just denote complete 3D stress representations, if I just show, then how we can write? Now, if I say, now all of you can see this one. It's better that if I draw once again here itself. Yes, just wait, I am telling you. Now, whether this particular cubical body is clear, all of you? This will be my x-axis. This will be my positive y-axis. Now, whether it is clear? The cube element which is being shown in the figure, whether it is clear? In the Cartesian coordinate system. All of you. Positive x, positive y, positive z, right? Now, this will be my negative x. This will be my negative y. This will be my negative z. Getting my point? According to our standard sign conventions. Now, if I'm removing this part, because right now you know that, right? Sorry. Right now you know that, so yes. If I just show like this, suppose for example here, what is this? On which phase this tau is acting? X phase. On which particular directions? Y direction, tau xy. This tau will be what? On which phase it is acting? On this particular x phase. In which direction? Positive z directions. Is that clear, this particular thing? All of you. Whether these things are clear? Tell me, guys, all of you. Now, if I just make it like this, if I just make it like this will be what? On which phase it is acting? On y phase. I told you what is the meaning of phase. Phase is nothing but the axis which is being passing through that plane in a perpendicular directions. That will become itself the phase, right? This particular, my dear friend, whatever the plane is there, which axis is passing? Y axis, right? So that will be the y phase. This will be the x phase. This will be whatever front you are showing. This will be z phase, right? Now, what will be the directions? Tau yx. What will be this direction, my dear friend? On which phase it is acting? On y phase. Which direction? Positive z directions. Whether these things are clear? How we are writing that? Tell me, guys. Any difficulties? Correct. Now, if I show my dear friend here, what we are calling this to be? And suppose, for example, here, or what we can call, just wait, just wait. Fine. If I so, yeah, correct. What will be the direction, my dear friend? On which face? Actually, when you see that it is acting on A, B, C, D plane. This tau is acting on A, B, C, D plane, right? Now tell me on which face it is acting? On negative x face, right? This will be the x. In which particular direction it is acting? In the positive y direction. Now tell me whether this thing will be positive or negative. This one. This will be minus tau xy. Getting my point? All of you are getting my point? Correct? Yeah. But my dear friend, for the stable or for the equilibrium condition of the body, for maintaining the static equilibrium condition of the body, what will be there? This direction will be reversed. Now you know the meaning of notation or sign conventions, right? So I'm just removing this part and I'm just reversing my directions. This will be the direction now. Now tell me what will be there? Tau xy, that is being positive. Getting my point? All of you understanding? If I just draw here, tell me what will be there? Whether this is acting on a what? Negative y phase. Sign for the plane. Which particular plane you not understood? Which particular plane you have not understood? Negative x. Here, when you see that here ABCD plane, ABCD plane, what is happening in ABCD plane? In ABCD plane, what is happening, my dear friend? When you just apply the parallel shear stress like this, then what we can write? It is acting on a negative x phase, right? It is acting on a negative x phase in which direction? Y direction. So ultimately, when you just write it, it will be written as what? Minus tau xy, that particular value. Getting my point? General sign convention for the plane will be what? I told you, right? The sign convention for the plane, the sign convention for the plane will be same as the sign convention of the axis, x, y, z. Whatever the positive x-axis is there, whatever the plane will be there, that will be the positive plane. That will be the positive phase, right? Now you see that here, this will be the negative y, right? In which direction, in which particular direction it is being acting? Negative y, y phase in which direction? X direction like this. So that will be minus tau xy. Getting my point? See, what is the y plane? What is the y plane? You tell me. Positive y plane means positive y axis which is being passing, right? Why this will be the negative y plane? Because negative y axis is passing. See that? Try to imagine the situation, right? This will be the origin. D point will be the origin. What is the purpose? See, if I show you the plane CD, let's say here this will be G, this will be H. Now tell me if I draw here this particular plane CD, GH. Now tell me which axis is passing perpendicular to this one. Which particular axis is passing? Negative y, right? It is a negative y. Suppose you have taken the body, this is the positive y phase. This will be negative y phase, right? Getting my point? Suppose you understood like this, x phase, that is a positive x phase, negative x phase. Is that clear? Positive x plane, negative x plane. Getting my point or not? Don't think that same axis. See, that's a very blunder. Some of you might be overthinking. What you're thinking, that this y-axis is passing same. You are thinking just like a pen. Y-axis just like a pen, which is being passing perpendicular to both upper y face and negative y face, right? Not like that. You just think like this. Which particular axis is passing? Getting my point? Tell me, guys. Which one? Which one you are not getting? CDGH. Where it will be the origin point? No, no, no. You are just thinking just like a mathematics, this cube element. You are thinking that it is on the horizontal plane, which is at the 0, 0 coordinates. That means maybe I got your doubt. You are thinking that we have defined like this y, right? Something like this, right? You are thinking like this plane, this one. If you just draw the 2D element, the y-axis will be like this and positive x-axis will be like this, right? And you might be thinking, sir, this will be the situation, right? Here it is passing through origin, right? The plane, horizontal plane. Tell me. Why you are thinking like that? Are you dividing the body like this? Or you are thinking that we are moving like this, all will be the positive value, here this will be the negative value. We are not measuring on a scale wise. I'm just telling that axis which is being passing through that specific plane, perpendicular plane, that's it. This particular axis will be this one. This particular axis will be what? This one. You will not say this y-axis will be the perpendicular to this one, right? Here, like this. Getting my point? No, 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 no. We are not shifting the origin here and there, right? Whatever the original coordinate system will be there, that will be the same coordinate system will be there. Any 3D element when you draw, let me show that. Any 3D element you will draw, it will be drawn like this only. See that? Getting my point? Whenever you draw the body, you draw suppose x-axis like this. So for this particular plane, suppose AB plane, you are drawing like this. Which particular, for AB plane, which is a perpendicular axis, x-axis, right? For CD plane, which is a perpendicular axis, this will be the negative x, right? You will not say for CD also positive x will be there. That is what, if you know the direction of axis, that will be the force directions. Plane is defining on a particular plane based on the axis which is being passing perpendicular to that particular plane. See, x-axis is passing, through AB plane, perpendicular. That will be x plane. We also call this to be x phase, right? I'm coming to your doubt. The doubt is very genuine doubt. Some of you might be thinking, if I draw this element, some of you might be thinking, sir, if I project my plane, this ABCD, it is being projected on which plane? YZ plane. Then why we are writing x plane, right? Some of you might be thinking this is a YZ, answer this direction will be x, then I should be writing like this. Whatever the sigma will be there, I should be writing like this. Why we are writing this to be sigma xx? To avoid the confusion, to make it very simple, we are simply representing not yz plane, we are simply representing by what? Phase. X phase or x plane. It is being defined like this only. Getting my point? That's a very basic doubt. I know that when you are studying this doubt will come, right? Don't think, once again I'm telling you, don't pass the line, this one, positive x-axis. You will say, sir, here also it is being passing like this, like this. That is a blunder. For this plane, what is the perpendicular? This one. For this plane, what is the perpendicular? This one. For this one, this one. For this one, this one. perpendicular away, which is passing away from that particular plane. That will be the plane. That will be the definition of the plane. That is a simple thing, right? Now, when you just take the total number of stresses, then what you will say? The total number of stresses will be 9. How? How it will be 9? Because when you just write 3D stress matrix, what will be there? Or let me write in a separate page. Now, just wait. Now, so try to think what is the direction of the shear stresses here. The direction of the shear stresses will be the sign convention for the shear stress is as follows. A shear stress is positive when it acts on a positive face of an element in the positive direction of an axis. Whether it is clear? Tell me, guys, all of you. If I just make 3D stress matrix, then what we can write? If we are writing tau x y, if we are writing tau x y, it is acting in a positive x space in a positive y direction. That means positive, positive. That will become what? Positive. If it is acting on a negative x space and on a particular what? Negative y direction, this will become what? Once again positive. And once again, just go back to mathematics. Very, very important school mathematics, right? Whenever we define the axis that is being perpendicular and away, that is become the axis, right? Don't be overthink that when the axis will be just like this, we define the axis like this. We never define the axis. Just go back to very, very school mathematics, or you just learn the 8th class, whatever the coordinate systems are there. That is a very, very weak, I can say. Right? Some of you might have confused completely based on the cubical element, whether it is a horizontal plane, whether you are shifting the origin. Basic element, if you follow basic coordinate system, it will be the origin x, y, z. Right? Simply x, whatever the y, x and z will be there, 0, 0, 0. That's it. That is the basic. Plus, plus, plus will be there. And whatever the things are will be there, that is a negative. And I don't know why you have the doubt when I said that it is a negative. That means whatever the plane will be there here, that will become a what? Whatever the plane will be there, that is a negative x plane automatically, right? Suppose here, whatever the stress will be there, this will be what? Negative x, whatever the x space is there, and on which direction? Negative y direction. This will become negative, negative will become what? Positive. So any value will be given in examination 10 megapascal, for example. Suppose here, it will be given as plus. So you have to show it like this. It is negative. If it is negative, we have to reverse the directions. Right? So before any starting of the topic, you have to tell me whether you know coordinate system or not. Right? Then only I can come to know whether you know or not about the coordinate system. Because that is a very basic fundamental, right? You might have done the engineering also. So you should be knowing the coordinate system. That is a very basic thing. Now, when you write the 3D stress matrix, then what we can write? Here we are writing what? Sigma xx. Then we are writing what? Tau xy, tau xz. And of course, don't write small letter. That is again blunder. That will be capital letter, because coordinate systems can be written only in what? Capital letters, right? Don't be write any small letter in the interview, right? This will be tau yx. Now, if I write tau yy also, then it will make any difference? Whether you will call this to be shear stress because of just symbol, tell me, or it will be the normal stress. Anybody can tell me whether it is the normal stress or shear stress if I just represent it by tau yy. Obviously, y phase and in the y direction, both are yy means what? Obviously, there has to be a y phase and y direction. That means it is a perpendicular. And perpendicular to which stress? Any stress which are perpendicular to the area, that will be the normal stress, whatever it may be the symbol, right? That will be the tau yz, tau zx, tau zy, sigma zz. Or let me write once again here also, otherwise some of you might have confused. So let me write sigma yy. Now here, indirectly, this row, first row is representing x phase. This is representing y phase, as you can see. Once again, just go back to the definition of the phases. Again, I'm saying that some of you who are having still confusion, you can just Google it. What is the meaning of phase? What is the meaning of plane? You can easily get the answer, right? Either you call x phase or x plane, both are same thing. Again, I'm telling you, I told you once again here also why we are not writing 3 suffix. We are representing only with the help of what? 2 suffix, to make it very simple. Otherwise 3 suffix will be there. You can see the complexity involved in the strength of material. To remove the complexity, we don't say this plane. If you project this ABCD plane, obviously it will be coming in the YZ plane, but we are not defining based on that. We are defining based on the axis which is being passing perpendicular to that ABCD plane. And which axis is passing perpendicular and away from that ABCD? That is a positive x. Once again, don't say negative x here. Whether it is passing away, no, it is coming towards. That is not the way of defining, right? Now, rather than asking the further doubt in that segment, you should be directly asking me the fundamental doubt. So I don't know the coordinate system, please explain me, right? Now, so now this complexity involved, this question has been answered. This is also one of the very famous question for sure, and only blank faces will be there at that time. So it's better that you just note down, right? We are defining the plane based on the axis which is being passing perpendicular to that plane. That is a simple meaning. Now, this will be the jet phase. Now, here this will be x direction. Second column will be the y direction. Third will be the z directions. Now you can simply say that why we are defining sigma xx, x direction, x, whatever the x phase, x direction. This is what? This is what? How to read that? X phase, y direction, x phase, z direction, y phase, x direction, y phase, y direction, y phase, z direction, z phase, x direction, z phase, y direction, z phase, z directions, right? Till now, this particular notations or whatever the directions are there, it has not been tested in gate examinations, because the moment if I give the matrix something like this, 10 minus 5 2 minus 5, suppose for example here I have given, for example I can take it as 0 minus 10 0 0 0 0. If I give this thing, and if I'll be basically based on this, if I frame 4 options A, B, C, D by cubical element representations, right? I can represent minus 5 tau xy like this in one option. In other option, I can show like this tau xy. Many of them will do the wrong. They might not be knowing this thing also. The directions of shear stresses. This is one of the, again, once again, a very, very fundamental thing. In theories of failure, directly I can give the matrix. I will be asking you what will be the factor of safety. Once again, that will be useful. The directions, the sign conventions. Once again, I'm telling you, this question has not been asked. Please make a note of it. This can be asked for GATE 2024. Right? Because hardly anyone focus on this particular topic, that usually what they used to say, that whatever the tau xy will be there, that will be positive when it is acting like this. Right? Here it will be like this. We tend to say that it is positive, positive, positive. All the things are positive. But we never understood why and how we are calling that shear stress to be positive. X phase, positive x direction, positive y phase, positive x direction, negative x phase, negative y direction, once again positive, because negative negative, once again it is positive. That's why it is our habit to not to think of that why the -5 can be shown, right? What you will think, this will be correct, but that is not true. All of you are getting my point? Tell me, guys. Even this fundamental thing I am telling you, not known to many one. Whether you know before or not known these things, it is well and good, but if you're not knowing, please make a note of it. I will show that whether you, if you're not knowing this thing, sign convention, how this answer will affected in the theories of failure, and that will be the very blunder, that will be out of the range answer you will be getting. Either you use the maximum shear stress theory, Tresca's theory, in that also you'll be getting the wrong answers if you don't know the sign conventions. Obviously, for the normal stress, everybody know that positive means it is tensile. -10 means that is -10 like this, that is sigma yy. But confusions are arises in the shear stress sign conventions. Is that clear? Can I move to the next one? Is it done, all of you? Tell me, guys. Now, so this is nothing but the 3 body, and in a 3D body, I told you how many total stress components are there. 9, right? That is what they have written. There are 3 planes, right? X, Y, Z. Each plane, one normal stress will be there, and 2 shear stress will be there, right? As you can see here, each plane will be considered to be as one. And once again, here also you should be correcting this one, this particular figure. This will be sigma xy. This will be tau. Which one? Positive x phase and z direction. So this will be xz. This will be xz. Right? So there are total 9 stress. The 9 stresses are there in a 3D body in terms of matrix, right? When the body is being subjected to complex loading conditions. Now tell me whether stress is a vector quantity or tensor quantity or scalar quantity. Because see, if I say velocity, that is a vector quantity. Why vector quantity? One magnitude 5 meter per second, and you will say that it is in the positive x directions. So what you will say? 5 I cap, right? You just denote it by only one subscript, right? Whatever the one subscript will be there, that will be enough, right? You say ux, only one suffix will be required. That is a vector. One magnitude, one direction. But in case of stresses, my dear friend, that is nothing but tensor quantity. What is the meaning of tensor? Anybody know that? More than one suffix or more than one particular suffix will be required, right? Now, what is the exact meaning of the tensor? Tell me, guys. Anyone know that? Yes, correct. Tensor means what we can have, which has the magnitude but multiple directions. A quantity which has the magnitude, and multiple directions. right? Yes or no? We will be required. Tensor means what? We have to only be, if we know in the directions, will it be sufficient enough? Whether we know the only directions, whether these things will be sufficient enough to tell about the stress? No, right? So tensor you can write one plane plus directions. Both will be required. Getting my point? We need to tell on which plane it is acting, in which direction it is acting. Getting my point? That's why it is a tensor quantity. Right? What is the meaning of vector? Only direction will be sufficient enough to tell that. Getting my point? Only one particular subscript, or what you can say suffix, will be required. You don't require u, x, y like that. No. Velocity in the y direction, what do you write? Uy. Velocity in the z direction, what do you write? Uz. But for the stress, will it be sufficient if I say sigma x? No, that is not correct. But that is a different matter of concern, that sigma xx sometimes can be written as sigma x only. But if I only say tau x, then can you say the direction of the shear stress? No. You define the plane, that is a positive x phase. On this particular phase, it will be acting. But now here or here, any possibility will be there, right? So if I say only y, then it will be like this. If I say tau x z, then it will be acting like this. Getting my point? So for tensor, we required one plane, one directions, right? Why 9 stresses? You can see here. If you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9 stress components are there, right? What are all those 9 stress components? Sigma xx, sigma yy, sigma zz. These are the normal stress component. And what are all the shear stress? Tau xy, tau xz, tau yx, tau zx, and then what we have? Tau yz and tau zy. This 6 component of the stress, that is a shear stress, and 3 normal stress, together it is constituted in what? 9 stress component, right? Getting my point? Negative phase stress. Which one negative one? That is a sign convention. Normal stress sigma xx, that is a normal stress only, right? That is a different thing whether it is a positive or negative. It can be anything, right? Now, next thing is that the principal stresses, right? Note down stresses in an inclined plane. That means here we will be starting the topic of principal stresses and strains. Basically, we are learning only principal stresses in this demo class. Now, very first thing is that why we are studying this topic called stresses in an inclined plane. That is the first thing. What is the physical significance of starting this topic called stresses in an inclined plane? Tell me, guys. Anyone know the reason for that? Why we are studying this? Now, so before understanding that, let me discuss the physical significance of, because the stresses on an inclined plane is directly related to principal stresses, right? Physical significance of principal stresses and strain. Try understanding what I'm saying right here. So suppose, for example, I have given example number one. One body is there which is fixed at one end, and it is being subjected to tensile load like this. Now tell me, if I will be asking you one question, what is that question? What is the shear stress value? What is the shear stress? What is the maximum shear stress in a body AB? Let's suppose if I have given the option A 0, B will be, I have given the option called P by A. C, if I give the option, let's suppose what? None of the above. Three options are there. Then what will be the answer? Of course, none of the above means shear stress is not equal to 0. Based on the loading condition, load is what? Perpendicular to the plane. Perpendicular to the plane, this one. 90 degrees there. And you know that when the load is acting perpendicular to the area, that will be the normal stress. There will not be any shear stress, right? So based on that, you can answer. I will be defining this to be BC plane, right? Now tell me guys, all of you please try to answer. Again, I'm telling you, whatever the things we are learning, definitely one question will be there from this demo class next year in the gate examinations. Now, see, let me ask one more question. Question number 2. What is the maximum shear stress? Because all of you might be knowing right now that shear stress means the stress which is being generated by the forces which are acting parallel to the area, right? What is the maximum shear stress on the plane? CB. Option A 0. Option B will be P by A. C will be none of the above. That means shear stress will not be equal to 0. Tell me guys, what will be the answer for question number 2? Now, so to answer these two questions, we have to study the physical significance of the principal stresses and strain, right? And that's what the concept of stress is defined at a particular point will come into the picture. I told you, right? Some of you might have disconnected at the moment when I said that the stress is defined at a particular point. But that thing will be clarified when you know the physical significance of this principal stresses and strain. Of course, we have not studied anything about this strain, so do not bother about that. I will be talking about the principal stresses only. Is that clear, all of you? Tell me, guys, whether it is clear. Now, so whatever the basic SOM equation is there, right? What is the meaning of basic SOM equation? If you say CB plane, and if you ask somebody, right, who might not be knowing the strength of material, what he will say, whatever the normal stress on BC plane is there, sir, we can able to find directly, and we know the formula P divided by area. That is a very basic, sir. We know the area, right? Based on the area, load divided by area, we know that that will be the normal stress. That will be the normal stress. Everybody know that. That is the maximum normal stress. But if I ask you the shear stress on BC plane, that is 0 because there is a no force which are acting parallel. There is a no force which are acting parallel to the BC plane. That means that is a 0. But if you say in a particular body, what is the maximum shear stress? That is, if you say 0, that is incorrect. P by A, that may not be true. None of the above, this will be correct. That means overall, I want to say shear stress in a body will not be equal to 0. On particular specific plane BC, in which only perpendicular load is acting P, because of that shear stress will be 0. But in a body, no. And that's why the play is there. That play is because of what? The definition of the stress. What is the meaning of definition of the stress? At a point. Stress is defined at a point. At a point means on this plane, one point has been selected, and that plane, one plane is passing what? BC plane. There might be some chances that it may be generated on this plane. which is being passing through that plane. That is nothing but C dash D dash plane. There might be possibility that EF plane, that stress will be generated. There might be possibility that this stress might be generated on this, what we call what, XY plane, right? Who knows that, right? Stress is defined at a particular point, and at a particular point, how many planes are passing? Infinite planes are passing, right? Now, why we are studying that principal stresses topic? Why we are studying this topic? Generally, tell me any material, if you just apply the load, it is failing because of the average stress or because of the maximum stress? Tell me, guys. Any material which are weak in shear loading, suppose it cannot able to resist that much of shear load, now tell me it is going to fail because of the maximum shear stress or minimum shear stress? You only tell me. Any material, if you just take, let's say ductile material, it is very weak in shear. Now tell me whether that ductile material will fail because of the maximum shear stress or minimum shear stress? Tell me, guys. Because of what? Maximum shear stress, right? Because of the maximum shear stress. And if any brittle material, if I take any brittle material, if I take, you know that brittle materials are very weak in tension. Little bit amount of tension you apply, it will fail. Just like a glass, window glass, if you just apply the load, it will fail. Then my dear friend, it will fail because of the maximum normal stress or minimum normal stress? You only tell me. Minimum. Why? 100 megapascal is there, 20 megapascal is there, because of which it will fail? Tell me. Maximum only. The moment maximum limit will reach, it will fail. That is the yield stress value, it is there, 100 megapascal. If you are applying the load beyond that, such that whatever the stress is generating more than the, what we call, ultimate point of the brittle material, ultimate stress point, it will fail. And now you know that you are telling me that this material, if I just apply what we call normal stress, it will not be fail. You want to say that means those who are answering this A option, that according to them, suppose this is a ductile material, right? This is a ductile material, my dear friend, and you are applying the tensile load. You want to say that, sir, this ductile materials are very strong in tension. It will never fail in whole life. You apply 10,000 Newton amount of load, it will not fail. Who said that? Ductile materials are very weak in shear, very weak in shear. It will fail because of the what? Maximum shear stress. And if you think that, sir, maximum shear stress in a body will be zero, just like that, and you will think that, sir, if it is zero, how much amount of load if I apply? The material will say, material will laugh, and he will say, I'm not going to fail. But you are wrong. Stress is defined at a particular point, and at a particular point, how many planes are passing? Infinite planes are passing. And who knows that on CD plane, maximum normal is maximum shear stress are acting, and on CD plane, the materials are failing like this. Same ductile material is failing like this. And what you said to the customer, that material will never fail. Now it is clear why we need to define one particular plane which is being inclined at an angle theta, and we need to find maximum stress, normal stress, and maximum whatever the shear stress will be there, the tau at theta value. Why we are finding that maximum value? Because ductile materials are very weak in shear. So to find the maximum shear stress, we are taking one plane at an angle theta, and we are differentiating after finding the equation such a way that we are getting the maximum shear stress on that plane, such that we can avoid the loading condition in the next cycle. We don't apply that much amount of load. We will be apply little bit amount of load, so that the maximum stress which is being getting generated will be less than whatever the permissible value. Getting my point? Whether it is clear why we are studying the topic called principal stresses, or we are saying that this stresses in an inclined plane. First, we are taking one plane which is being inclined at an angle theta, and we are finding one equation sigma and theta, tau is theta, and then we are saying that these equations will be giving me the stress value at a particular plane which is being inclined at an angle theta. Getting my point? Tell me, guys. And now it is directly connected to the point which I mentioned earlier, is stress is defined at a particular point. That's why, that is also the reason why we say stress is defined at a particular point. Whether these things are clear? Tell me guys, all of you. Tell me guys, why I said this thing. If I directly start stresses in an inclined plane, and if I say directly this equation, these are the equations to find the stresses on an inclined plane theta, that is a shear stress, directly use this equation, you will be getting the answer. Suppose you know the plane angle on which maximum normal stress is there, right? What you will say, so theta value I will put in this equation, I will be finding the maximum normal stress, because brittle materials are very very weak in tension. Again, that for the ductile material, you will find one plane on which maximum shear stress is acting, right? That theta value, theta 1 value, you will put here, and you will say, sir, I found out that maximum shear stress. Now we cannot apply that much amount of load. We need to lower down. If I directly tell you, whether you might be understanding or not, no, you will not understand. That's why I'm saying before only the physical significance of this topic. Getting my point? After the class, once again you go through these videos 2 times, 3 times. Definitely you will be understanding something. These are the very basic thing which I'm discussing. Hardly you will find any of the books which are local author books. You will find in what? Gear and Godno or Hibler, right? So try to understand these things. And again, I'm saying you that whatever the things we have learned in demo class only, one question will be there in examinations. Because nowadays the play is because of what? MSQ. Earlier days only we have MCQ, right? If you know little bit concept also, that will be okay. But now if you know, until unless you are not knowing top to bottom thing, you cannot answer MSQ. And if that would be the negative, that will be a more challenging one. But unfortunately, that is what? No negative marking for that. But soon, to make the competition more a little bit, no, to basically to create more competition, they may create the negative answer for MSQ also, just like JEE Advanced, what we have, the pattern. Anytime soon, whatever the syllabus will be there, a pattern will be there, that can be released. Till now, MSQ, no negative marking is there. But just like I mentioned that in JEE Advanced, we will be having, already we have seen that in MSQ, we will be having what? Negative marking. Right? One option is correct, more than one option is correct. Until unless the fundamental is clear, you cannot answer, even though you practice 1,000 numerical on that particular topic. Right? Now, whether these things are clear or not, guys, tell me, so that we can start our discussion. Right? So on a BC plane, obviously that is 0. This option is correct. But for a particular body in a body, that is not equal to 0. Right? Now, note down this particular diagram. Now, notations are very, very important. Here, whatever the sign convention which I will be mentioning, that is once again very, 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 very important. So don't think like this to be a very, very demo class where we are not discussing any important topic. I told you one question will be there. Already YouTube session will be there. Next year also this same video will be there. Again, I'm telling you the proof. One question will be there from this session. Why? Because that is what motivates you to basically see this video, right? Or maybe attending these classes. Now, we need to define one plane. This is a what? Plane on which tau xy is there, sigma. Now, some of you might be thinking, sir, this is what 2D stress, isn't it? Whether it is a 3D stress, tell me. Where is the third dimensions? Sir, you are showing only in X direction, in the Y direction. Where will be the third directions, right? Our earlier case, what we have discussed like this. That was the 3D case. Now, that was the 3D particular stress, right? 3D element. This is what we have 2D element, right? On a particular 2D element, what we are saying. Now, how to convert 3D element to 2D element? How to convert 3D element to 2D element? That means if you are just writing 2D stress element, only 4 component will be there. Sigma xx, tau xy, tau yx, sigma yy. Only 4 components of the stress will be there. Now, what about the other components which are acting in the z directions? Tell me guys. In which case we can assume 3D element to 2D element? How we can convert 3D element to 2D elements? My dear friend, understand, in any body, when thickness will be very, very small, that means when the thickness will be very, very small, like this. A very, very thin lamina body when you take and you are just applying the load like this, for example. Same cubical element. Same cubical element, if I say X, this will be Y, this will be my Z. Same thing I'm saying, X, Y, Z, whatever the things are there. Here, you try to understand. Suppose this will be the dimension A. This will be the dimension A. Thickness is T now. Earlier it was A. But now I have reduced the third dimensions which are acting in the Z directions, right? In Z direction, whatever the dimensions are there, I have reduced it. Now it is thickness T. T is less than A, very, very small than A dimensions. A thin lamina. A thin lamina. In this particular thin lamina, my dear friend, what we are neglecting, whatever the sigma zz is there, which are acting perpendicular, that will be very, very lesser than sigma xx and sigma yy. Agree with me? How? How? What is sigma zz? The load which are acting force divided by area. Divided by area, right? Sir, what about sigma xx? Force which are acting in the z direction, force which are acting in the x direction divided by area. Now tell me what is the area on which it is acting. Let's suppose force is what? Fx. What is the area, my dear friend? Area, what is the area? Can I say A into T? On which it is acting? Correct, A into T. What about this area? A into A. Now tell me which area will be larger. This area will be very, very large as compared to this area. That if this area will be very, very large, sigma zz will be very, very small. Sigma zz will be very, very small. Similar argument will be happening for tau xz also, tau yz also. That will also be 0. One possibility of converting 3D element to 2D element of basically what 3D stress element to plane stress problem, if you want to convert, what is going to be there? Whatever the stresses are there which are acting in the third directions, that will be 0. Here I'm assuming third direction is what? Z direction. Either area will be very, very large or forces will be very, very small in that particular dimensions, in that particular directions. Forces will be very, very small as compared to forces in x direction, forces in z directions. Why we are applying little bit amount of forces? Because that much of dimension is not there to resist that load. Even though that is a discussion of plane stress and plane strain condition. Why I'm putting that discussion into here? Because some of you might have not confused. So earlier you have taken 3D stress element, now you are drawing only 2D stress element. How it is possible? Where will be the third dimensions? And that is what we are converting. Thickness is such a very, very small, you can neglect that, and in a 2D view we just show like this. Getting my point? How this particular picture is coming, whether it is clear? Tell me guys. Yes. Tell me, guys, whether it is clear how to convert 3D stress element to plane stress or 2D stress element. Tell me, guys. Whenever thickness of the element is very very small, then whatever the stress will be generated in that thickness direction will be neglected, either normal stress or shear stress. Getting my point? Tell me, guys. That is also one of the MSQ. If I ask you at this point of time one question, can we convert 2D stress element into 3D stress element? If I say one question, suppose one question is there, can we convert 2D stress element into 3D stress element? Tell me, guys. Yes. B option is no. Now, if your object is, my dear friend, if your object is something like this, where you're applying the sigma yy here, sigma xx here, and here you are applying, suppose tau xy, here you are applying tau yx, something like this. If that is the situation, that if particular element is there, stress in z direction is what? Zero. That means sigma fz is zero. Whatever the tau yz is there, all the things are zero. On this ABCD plane, what we can have? Tau, positive z phase, and y direction. This will also be zero. Right? Now, understand. If this is your element, right? This is your element. What we are calling this element to be? Where only the forces are there in the what? X phase and Y phase. There is no force in the Z phase. That is also 2D stress. That is also a 2D stress, right? If you just write 2D stress element, it will be sigma xx, tau xy, tau yx, sigma yy, right? When you write that, once again it is clear that whatever the forces are has been applied in the third dimension, z direction is zero. We can convert that particular 2D stress element into 3D by just applying the forces in z directions. Everything is will be clear. You have to apply little bit larger amount of force. Very good. Whatever you answer, that is correct, right? When you just apply little bit large amount of force, you can convert this 2D element in which only the forces has been applied in the two directions, not in the third directions. Still, you can convert it by applying the forces in the third directions. But your 2D stress element is like this, where thickness is very, very small. Even though you apply forces, how large forces, you can never convert this particular 2D stress element into 3D stress element. Right? So now tell me which option will be correct. That will they can given in the form of what? Statement A, B, C, D, Q, A, B, C, D. Getting my point? So these are the few things that we'll be exploring in the few basically what in the full course. In the particular demo, as we have the time constraint, so I cannot go into the deep of that, but you try to understand what I want to say. Getting my point or not, all of you? Plane stress means in the two directions the forces has been applied. Biaxial state of stress conditions, what we are calling 2D stress, plane stress, biaxial stress, all are same thing. Only the stress will be generated in the two directions, x and y. Maybe x and z, y and z, any combination will be there. Is that clear? Tell me, guys. Whether it is clear? Because in earlier case, even though we have the thickness, that is a comparable as compared to other dimensions. So even though you apply the force, it will able to resist. But here thickness is very, very small. It cannot resist. It will fail. Right? Because if you keep on applying the forces, large amount of forces, automatically in X and Y forces will also be affected. Right? Now, so note down the stress transformations. Note down the stress transformations. Suppose we want to what? Transform the axis, right? Suppose you have the plane like this. You have the plane stress condition like this. And you have been given sigma xx, sigma yy, sigma yy, sigma xx, right? Now, why I'm writing this to be positive here? There should not be any doubt, right? Negative x phase, negative x direction. Negative, negative will become positive, right? Here I'm just taking what? Tau xy here, like this. Like this, right? And once again, tau xy will be equal to tau yx. How and why? Do not bother about that as of now. We will be learning in the full course. Here you just understand tau xy will be equal to tau yx, right? Because of movement equilibrium. Right? Now, suppose I need to find the stresses on this plane. On this plane, which is being inclined at an angle theta like this. On this plane AB. How we can able to find? I need to find what is the normal stress and what is the shear stress. I need to find what is the normal stress and what is my shear stress. I need to find these two things on this AB plane. How we can able to find? By using this stress transformations, right? But for this plane, my dear friend, let's suppose this plane is here like this, right? This plane is here like this, right? Now this plane, what is the axis which is being passing? Earlier the axis was x and y like this, right? X and y was like this, right? Or let me write with the capital letter. Now, when you just write the axis capital letter X and Y, when you try to rotate this body in the anti-clockwise direction theta, what is going to be happening? What is my x-axis? This will become what? This will become S. This will become what? T, for example. Right? Or you can also say this will be X dash. X will be converted to what? X dash. And T will be converted to what? Y dash. Because all the axes will be tilted by the same amount. All the axes will be tilted by what? With the same amount. Theta in the anti-clockwise direction. Whether these things are clear or not, tell me. Tell me, guys. Now, if you want to find what is the normal stress on sigma at this particular plane AB, then how you can find? Just use this equation. What they have mentioned, sigma x or sigma, what we call x dash. How we can write? C square sigma xx plus s square sigma yy plus 2cs sigma xy. Sigma xy is what? Sigma xy means tau xy. Now put that value, see, cos square theta sigma xx plus sigma yy sin square theta plus 2 tau xy, or rather than I can write sigma xy cos theta into sin theta. Further, if you simplify, what you will be getting? Further, if you just simplify this one, what you can write? What you can write, my dear friend? Let me remove this part. Now, further, if you want to write, how we can simplify this one, how we are basically arriving at this conclusion. So what we have written, sigma s, sigma xx cos square theta. Same is the same thing I'm writing here. C is what? Cos theta, and S is what? Sin theta, right? Now, same thing I'm writing once again to the next slide, right? Sigma yy plus 2 tau xy, or sigma xy sin theta into cos theta. Now, my dear friend, tell me what is the formula for cos square theta? 2 cos square theta minus 1, that is what? Cos 2 theta. Getting my point? 1 minus 2 sin square theta, that will be what? Sin cos 2 theta, right? Cos 2 theta. So put that values. Sigma xx, that will be 1 plus cos 2 theta divided by 2. Sigma yy, 1 minus cos 2 theta divided by 2. 2 sigma xy, or sin, what we know the formula, 2 sin theta cos theta will be what? Sin 2 theta. So that can be written directly. That can be written what? Sin 2 theta, right? So here sigma s can be written as, if you just combine sigma xx, so what you can write? Sigma xx plus sigma y by 2 plus sigma xx minus sigma y by 2 whole into what? Cos 2 theta plus sigma xy into what? Sin 2 theta. And that is what you are getting the formula. Same formula. Similarly, tangent stress or shear stress you can find, right? Shear stress you can find on this element like this. Sigma st can be written as directly minus sigma x. See, if you just multiply here sigma st, right? You can write sigma st is what? Minus cs into what? Sigma xx plus cs sigma yy plus c square minus s square into what? Sigma xy. If you once again, if you resolve into the formulas, you will be coming this. You will be what? Arriving to this particular conclusion. So these two formulas are very, very important. And on this plane, sigma s is there, sigma st is there. Then what is the resultant stress? The resultant stress will be this one, under root of sigma s square plus sigma st square. And what is the angle of obliquity? Angle of obliquity will be tan inverse of sigma st divided by sigma s. That means like this. We just find the angle, then what will be the angle? This will be the phi, where it is what? This component will be what? Sigma st, and this component will be what? Sigma s. On this plane AB. I'm talking about the plane AB. Getting my point, all of you? Please make a note of it. Now, so we got the formulas of what we call what is a normal stress on a particular plane and what is a shear stress on a particular plane, right? I think we can discuss up to this point. All of you understanding or not? All of you understood this particular session? First, what we have learned that what is the basically definition of the stress, right? What is the physical significance of the principal stresses? Why we are defining the stress at a particular point? Why this stress is about tensor quantity? Now, some of you might be feeling that I'm moving very fast, but of course, each and every discussion will be doing minute discussion will be there in a particular what? In a slow manner. Don't be think that in a regular classes it will be that much fast. Here we have little bit of time constraint, so that's why. And I have not basically understood your doubt, right? That's why maybe some miscommunication might happen, but those things will be clarified when we'll be discussing each and every topic in individual classes. Getting my point? I just want to make sure that you understand what is the meaning of stress actually. What is the meaning of internal resistant forces? That is a very basic fundamental thing that will be neglected actually by most of the students, and that's why they face the difficulty in strength of material, especially by aerospace student. Even though you ask the topper of the aerospace first ranker, if you ask whether you have scored full marks in strength of material, he will say no directly. That's why I'm saying that please pay some little bit of attention and please be patient. Each and everything will be clarified, and you will be able to answer full lot of full marks. That is my guarantee. Right? Thank you all.
Yes, Rahul sir. I think guys, sir got disconnected. So we will wind up today's part here, and we will do one more session. So okay, because still sir have some part pending, so we'll do in part two. Okay, some other day. So thank you all for joining this session. Hopefully it was good and it will be helpful for many of you. Thank you all.